This time we're going to look at the derivation of the formula for the bandwidth of a non-inverting op-amp amplifier. Starting from the beginning again, supposing if we have a op-amp like this, that's our input voltage. We have a potential divider here, and that's our feedback signal. I'll call that RF, and this R2, and that's my output voltage. Now, the op-amp, if we're in the stable region, will be acting to try and produce an output, which is the open loop gain times the difference between its two inputs. So I could write that Vout is equal to A, the open loop gain, times Vin, minus the voltage at the inverting input here. But the voltage at the inverting input here is the output of this potential divider, and that's just equal to Vout times R2 over RF plus R2. If I do some algebra on this expression, I can get that Vout is 1 plus the open loop gain times R2 over RF plus R2. That's equal to the open loop gain times Vin. And therefore the gain of this amplifier, Vout over Vin, is going to be the open loop gain divided by 1 plus the open loop gain times R2 over RF plus R2. And previously we just proceeded from here by saying we could assume that the open loop gain A was practically infinite. And that's a good approximation at low frequencies. But as we move towards higher frequencies, we can no longer make that assumption. What we can do is assume that the open loop gain is accurately given by the new dependent source model of the op-amp we looked at earlier. The open loop gain is the open loop gain at DC divided by 1 plus J times F over FB, where FB is a characteristic frequency of the op-amp. I've called it FD on the slide here. Let's be consistent. FD. The D stands for dominant, by the way. Comes from an approximation called the dominant pole assumption that we'll be discussing in a few videos' time. Right then, substitute this into here, and we end up with Vout over Vin. The gain of our op-amp is the open loop gain at DC divided by 1 plus JF over FD, all over 1 plus the open loop gain at DC divided by 1 plus JF over FD, times R2 over RF plus R2. I can simplify this a little by noting that RF plus R2 over R2 is equal to the gain at low frequencies, which I'll call GDC, the gain at DC. Then multiplying top and bottom by 1 plus JF over FD gives me A times DC, all over 1 plus J times F over FD, plus ADC divided by GDC. Or in other words, the gain at DC divided by 1 plus GDC over ADC times 1 plus JF over FD. And I've just multiplied top and bottom of this expression by GDC over ADC to get from here to here. Now, multiplying out this bracket gives me GDC over 1 plus GDC over ADC plus J times F over FD times GDC over ADC. Now, ADC is the open loop gain at DC. It's a very, very large number. For the op-amp that we saw last time, it's about 200,000. GDC is the closed-loop gain, the gain of our amplifier circuit at low frequencies. And that's unlikely to be any more than about 100 or so. Therefore, GDC over ADC is going to be very, very small, certainly much smaller than 1. Neither of these are functions of frequency. So we're quite safe to just neglect that term, because it's always much smaller than a 1. This term, however, we can't neglect in the same way, because f, the frequency, could be very large. And it's entirely possible that f times GDC might be just as big as FD times ADC. So to a good approximation, I can write the frequency-dependent gain of my non-inverting amplifier as GDC divided by 1 plus J F times GDC over FD times ADC, which is the formula that I've ended up with here. If I just take one further step, I can end up with this formula here, noting that FD, ADC and GDC are constants for my circuit. So this formula now looks like it's in the same form as most of those frequency response formulas that we've seen before. And we've plotted them like this, and they start at the maximum gain and they go down, and the 3 dB point is the value of this term here. So we can immediately identify FB, the 3 dB frequency of our amplifier, as being FD times ADC divided by GDC. We'll see that the 3 dB bandwidth of our circuit is inversely proportional to the gain of our op-amp amplifier. And that's a very interesting, useful and important result. The gain at DC multiplied by the 3 dB bandwidth, FB, that's just the 3 dB bandwidth, is equal to FD times ADC. And both of these terms are characteristics of the op-amp itself. ADC, the gain at very low frequencies, at DC. FD is where the open loop gain starts to fall off for that op-amp. They're not a function of the particular circuit that you put it in. They're not a function of the resistors or any other component in the circuit. They're purely a function of the op-amp itself. And it's such a useful value to know that it's given a particular name, and you'll often find it specified on op-amp datasheets. It's known as the gain bandwidth product. So called because it's the product of the gain and the bandwidth, at least for non-inverting amplifiers. This gives us a very simple way to calculate the 3 dB bandwidth of a non-inverting amplifier, knowing the characteristics of the op-amp and the gain that we want our amplifier to have. For example, consider the circuit. It's an op-amp amplifier with a gain bandwidth product of 20 MHz. And if we wanted to calculate what the 3 dB bandwidth of this amplifier should be, then we could simply use this formula. The gain at DC, well, this amplifier has a DC gain of 5, times the 3 dB bandwidth, that's what we're trying to work out, is equal to the gain bandwidth product, which for this op-amp amplifier is specified at 20 MHz. Therefore, FB, the 3 dB bandwidth of our amplifier, would be 4 MHz. And we can always check and see if the simulator agrees. Well, at low frequencies, this amplifier has a gain of 5. Therefore, if we're looking for the 3 dB bandwidth, we want to know what the gain would be if it was 3 dB less than 5? Well, that would be given by minus 3 equals 20 times log to the base 10 of some output voltage divided by 5. That would tell us what the output voltage would be when we're 3 dB below 5. It's just the ratio of the output to the output at low frequencies expressed in terms of dBs. Work that out and we get 10 to the power of minus 3 over 20 times 5, 3.54. So the frequency at which the output is 3.54 volts would be the 3 dB frequency in this case, be the frequency at which the gain had dropped by 3 dBs. Let's try and find it. Okay, that's about it there. At 3.989. Okay, let me set the frequency to exactly 4 megahertz and see what happens. 3.536. Let's see what 3.536 would be in terms of a decibel drop on its low frequency gain. That would be 20 times the log of 3.536 divided by 5. Yep, that's just about 3 dBs. It's interesting actually. This is very, very close to minus 3.0103. And that is actually the drop that we usually refer to as 3 dBs. It's a factor of 1 over root 2. Remember when we calculated the 3 dB bandwidth, what we call the 3 dB bandwidth is really the frequency at which the amplitude is dropped by a factor of 1 over root 2. And 5 divided by the square root of 2 is 3.535, which is pretty much exactly where we are. So yes, within the accuracy that we're working to, this looks pretty good. The formula is predicting the 3 dB bandwidth accurately. Next time, we'll have a look at inverting and summing and differential amplifiers.